Welcome to Lecture Cast, where we discuss general chemistry topics. This is a podcast lecture series on general chemistry. Today, we will be talking about chemical equilibria. My name is Mr. Ferguson. I am a young faculty, and I'm also an associate member of the Royal Society of Biology and an associate member of the Royal Society of Chemistry. Hello and good evening, everyone. What a moment where everyone is on their feet, holding a flag and supporting their concept. Team Equilibria on one side of the field and Connects on the other side of the field. Now, let's get ready to rock and roll. These two experimenting concepts exemplify in the spirit of chemistry that skill displayed in different ways, perhaps, but by world-class chemists again. There is history to be made or added, concepts to be learned, and skills to be gained. Just before we begin, just before we dive into the concepts, I want to remind everyone you are not alone. This is an academic community. Remember to get help when needed. Reach out to university services if needed. Never give up. Keep trying. We are here to help you be intelligent, ethical, and responsible scientists. But at the end of the day, you must be responsible, ethical, and hardworking. So let's talk about Le Chatelier's principle. When a system at equilibrium is disturbed by a change in the amount of a reactant or product, a change in volume, or a change in temperature, the system shifts in the direction that minimizes the disturbance. So a quick overview, we'll discuss the equilibrium constant. Remember the word extent. We'll talk about dynamic equilibria. Remember a treadmill. The equilibrium constant expression. Remember the law of mass action. The equilibrium constant. States of matter and the equilibrium constant. Calculating K, the reactant quotient, K and pressure, find the equilibrium concentrations, and the Chatelier's principle. These are just a few of the topics we will cover. In some of these topics we will cover today. The rest we may cover in later episodes. So the equilibrium constant. The relative concentrations of the reactants and the products at equilibrium are expressed by the equilibrium constant K. Let me say that again. The relative concentrations of the reactants and the products at equilibrium are expressed by the equilibrium constant K. One more time. The relative concentrations of the reactants and the products at equilibrium are expressed by the equilibrium constant K. The equilibrium constant. The equilibrium constant measures extent. How far a reaction proceeds towards products, how far a reaction proceeds towards a specific point. So a large K, much greater than 1, indicates a high concentration of products at equilibrium. A large K, much greater than 1, indicates a high concentration of products at equilibrium. The equilibrium constant measures extent. How far a reaction proceeds towards products. A small K less than 1 indicates a low concentration of products at equilibrium. Dynamic equilibrium. Most chemical reactions are reversible. They can proceed either with the forward or the reverse reaction. Depending on the type of reaction you're referring to, certain steps may be more or heavily weighted. When a chemical reaction is in dynamic equilibrium, the rate of the forward reaction equals the rate of the reverse reaction, so the net concentrations of the reactants and products do not change. When a chemical reaction is in dynamic equilibrium, the rate of the forward reaction equals the rate of the reverse reaction, so the net concentrations of the reactants and products do not change. One more time. When a chemical reaction is in dynamic equilibrium, the rate of the forward reaction equals the rate of the reverse reaction, so the net concentrations of the reactants and products do not change. So dynamic equilibrium. However, this does not imply that the concentrations of the reactants and the products are equal. So a reaction being at equilibrium does not imply that their concentrations of the respective reactants and products in that reaction are equal. Now let's talk about the equilibrium constant expression. The equilibrium constant expression is given by the law of mass action and is equal to the concentrations of the products raised to their stoichiometric coefficients divided by the concentrations of the reactants raised to their stoichiometric coefficients. So when you look at the reaction, you see that there are numbers in front of those chemical symbols, those are typically referred to as the stoichiometric coefficients. So when you write an equilibrium constant expression, you put the concentration of the reactant in brackets, in square brackets, and the exponent for that square bracket term is the stoichiometric coefficient, and it's products over reactants. So also, the equilibrium constant can be expressed in terms of concentrations or in terms of partial pressures. Remember the relationship between pressure and concentration within the context of moles? The two constants are related. Concentration must always be expressed in units of molarity for Kc. Partial pressures must always be expressed in units of atmospheres for Kp. The equilibrium states of matter and the equilibrium constant. The equilibrium constant expression contains only partial pressures or concentrations of reactants and products that exist as gases or solutes dissolved in solution. Pure liquids and solids are not included in the expression for the equilibrium constant. One more time, the equilibrium constant expression contains only partial pressures or concentrations of reactants and products that exist as gases or solutes dissolved in solution. Pure liquids and solids are not included in the expression for the equilibrium constant. So calculating K. We can calculate the equilibrium constant from equilibrium concentrations or partial pressures by substituting measured values into the expression for the equilibrium constant as obtained from the law of mass action. So what does this mean? We can calculate K given the concentrations or partial pressures when we have those measured values. As we progress in this discussion, we'll also in later episodes we'll introduce the idea of using ice tables in which you look at the initial change in equilibria concentrations. You look at what you start off with, the change, which can be denoted by some x, some variable term, and then you net, or the net expression will be the initial minus the change, and you use those terms at the bottom. The E section of the table, use those terms, you form an expression using the law of mass action, and from that expression you equate it to the known equilibrium constant, and you solve for x, and you're able to obtain the different concentrations of the reagents at different points in the reaction in order for you to progress and solve the problem. So calculating K. In most cases, we can calculate the equilibrium concentrations of the reactants and products, and therefore the value of the equilibrium constant from the initial concentrations of the reactants and products and the equilibrium concentration of just one reactant or product. So one more time, in most cases we can calculate the equilibrium concentrations of the reactants and products, and therefore the value of the equilibrium constant from the initial concentrations of the reactants and products and the equilibrium concentration of just one reactant or product. Now, depending on whether the type of substance or reaction that you're referring to, that may be easier said or easier done. So you really have to know the reaction, understand the reaction that you're referring to. For example, with strong acids and strong bases, it's very easy or relatively easy when compared to weak acids and weak bases. So if say you have the equation is A plus B turns to C plus D, where the stoichiometric coefficient of A is little a, the stoichiometric coefficient of B is little b, the stoichiometric coefficient of C is little c, the stoichiometric coefficient of D is little d. That will be, if you're looking at the video that will be posted eventually, it will be capital C in brackets raised to lower c, capital D in brackets raised to little d over capital A in brackets raised to little a, and capital B in brackets raised to little b. And this is derived from the concept or the expression in which you denote terms that state or show that the forward rate is equal to the reverse rate. So the reaction quotient. The reaction quotient, Q, is the ratio of the concentration or partial pressures of the products raised to their stoichiometric coefficients to the concentration of the reactants raised to the stoichiometric coefficients. And the key thing to remember, the difference between Q and K is Q is at any point in the reaction. K is at equilibria. So, It's important to know the reaction coefficient, the reaction quotient is at any point in the reaction. The equilibrium constant is at K. At K. The reaction quotient is the ratio of the concentration or partial pressures of the products raised to the stoichiometric coefficients to the concentrations of the reactants raised to the stoichiometric coefficients at any point in the reaction. The reaction quotient, like K, Q can be expressed in terms of concentrations or partial pressures. At equilibrium, Q is equal to K. Therefore, the direction in which a reaction proceeds can be determined by comparing Q to K. One more time. At equilibrium, Q is equal to K. Therefore, the direction in which a reaction proceeds can be determined by comparing Q to K. If Q is less than K, the reaction moves in the direction of the products. If Q is greater than K, the reaction moves in the reverse direction. If Q is less than K, the reaction moves in the direction of the products. If Q is greater than K, the reaction moves in the reverse direction. So finding equilibrium concentrations. There are two general types of problems in which K is given and one or more equilibrium concentrations can be found. For the first type, you have the equilibrium constant given and all but one equilibrium concentrations are given. We solve this type by rearranging the law of mass action and substituting the given values. For the second type, K and only initial concentrations are given. We solve the second type by creating a nice table and using a variable x to represent the change in concentration. And depending on our equilibrium constant, whether it is smaller than 10 to the minus 5, we can use the x as small approximation. When you do the x as small approximation, whatever you subtract x from, the ratio of those things when multiplied by 100 should be less than 5%. If that's not the case, the approximation won't be as sound. There are two general types of problems, again, in which K is given and one or more equilibrium concentrations can be found. First type, K and all but one equilibrium concentrations are given. We solve this type by rearranging the law of mass action and substituting the given values. Second type, K and only initial concentrations are given. We solve the second type by creating an ice table and using a variable x to represent the change in concentration. Equilibrium is so important. When a system at equilibrium is disturbed by a change in the amount or reactant of a reactant or product, a change in volume or change in temperature, the system shifts in a direction that minimizes the disturbance. So, ladies and gentlemen, it was an exciting match. At the end, the scoreless first half and 3 huge goals in the second, including the Chatelier's winner at the wire. The Classical goes Equilibria's way on enemy ground, and all the reactions continue until we meet again for the Classical Acidica and Basisio. Hope you're doing well. Hope all is well. Continue to read, continue to study, continue to prepare. This is just a preview of more to come in terms of equilibria, acids and bases, dynamic equilibria, and other concepts associated with thermodynamics.